give you, remember, 15 questions. 15 questions, 2 types. So let me give you one by one. So each question, what type it is. Yeah. So, all right. So then you can do preparation. Focus on these types. All right, so first, R1.1, question types for solving ODEs. Computation, not word problem. Yeah. Second part of word problems. Yeah. All right, first part, we will have 7 questions. Yeah. The first one, question number 11. Okay, yeah. So after first 10 questions. Yeah. Number 11. Yeah. Extended separable ODEs. Yeah. So we jump to that extendable separable ODEs. Here I give you 2 examples. So these 2 we did in class. Yeah. So these 2, yeah, here let me, the point here. These 2, they have 2 special formats. Yeah, so you need to recognize these 2 special formats. The first one, yeah, you need to, first take division. Yeah, try to write a standard form for the first order ODE. So you divide it by 2xy both sides. So you get so y prime equals y squared 2xy x squared 2xy. You can do some simplification. Y over 2x minus x over 2y. Okay? All right. So here the format. The format for the first type should be f of, y over x. Yeah. So there is a chat message. Let me check it. Chat message. Yeah, only I can see on this computer, not the other 2 computers. Yeah, let me try to look at here. Chat message. Chat. Yeah. Here. Both both. All right. Oh, same problem last time. All right. Thank you reminding me. Let me off. Yeah. Okay. Yeah. Yeah. Thank you. Yeah. Yeah. All right. Yeah. So this format, f function of y over x. Yeah. So the first type. Yeah. All right. Yeah. Second type. Inside parenthesis, it is ax plus by. Yeah. Format. Yeah. It's like ax plus by format. Yeah. Then you can treat this parenthesis as a new variable, or this function you can write as a f function of ax plus by. That format. Yeah. So both these formats we can easily by introducing a new variable here, just a u u equals ax plus by substitution, so you can make it separable. The second, u equals y over x, make it separable. So I cannot give you both. I can only give you one of the two in a test, because we have too many question types to cover. So each type I can only take one question. All right. It's very likely the second one, okay, not the first one. Second type, not the first one. Yeah. But the first one, the background of the first one, you need to answer some questions in the first 10. Remember the first 10? Concept questions, so you need a background of the first type. Yeah. Remember, in the last class, I gave you example that's closely related. Yeah, let me remind you. Y prime equals P of xy over Q of xy. Remember that question I talked about last time? P xy, basically a n y n plus a n minus 1 y minus 1 x plus dot dot dot. All right? Yeah. Q b n y n b n minus 1 x plus dot dot dot. Okay? All right. That one. Can you see the P polynomial over Q polynomial can be written as a function of f of y over x? Can you see that? Can you see that? Some f function with, y over x format. So Julie, you can see? Yeah, good. Good. Because that's the main point. That if you can see this structure, then you can answer that question easily. Okay? Yeah. Yeah. So you need to use the knowledge we learned in a very, flexible way. Yeah. So it's not a dumb way. Okay? Yeah. So very flexible. Yeah. Here, there, whenever it is needed, you just use your knowledge. Yeah. Like this one. Yeah. All right. Yeah. So that's the first two question examples. MQ11. Second one, MQ12 question type. Reduction to exact form. Yeah. Here we have several examples. Yeah. This one we did in class. Yeah. The question, it is not exact. Yeah. At the beginning, it is not exact, but we need to find a integrating factor. But we have formula to find it, right? Yeah. Two options, R, capital R, and the capital R star. Yeah. All right. So then, in the exercise, we have these two more. So here I just give you sample questions like these three. Yeah. Yeah. I plan to compile, a document containing all these question types with, sample questions, solutions, main formulas. Yeah. So when you do preparation, because I try to save your time to make your study more efficient. And in the test, you use that document, you can find the related formulas quickly, right? Yeah. one by one, it's like in order. Yeah. Try to save your time. Yeah. But you need to practice by yourselves before the test. Yeah. All right. Yeah. So these three. I haven't uploaded this PowerPoint slide, but I will upload. Yeah. So you may not need to write down everything. Yeah. So because I will upload after the class. Yeah. All right. Otherwise, could be very slow to follow. Yeah. Next question. Number 13. Non-homogeneous linear ODE. Yeah. Like this one. So we have a formula. PXRX. Yeah. So the formula we use, this is a P of X function, R of X function, and we have a formula. Yeah. So you just, use the formula. Yeah. Here, so this one, you can see you can convert it to the standard form first. Yeah. Standard form, P of X and R of X. Yeah. Yeah. So you need to recognize the type. Yeah. But here it's not hard. Yeah. Recognizing the question types, because in my document I give you in order. Yeah. So you just follow the order in the document. So the type's already there. Okay, formulas already there. Yeah. But you need to do the computation carefully. Yeah. All right. So that's the number 13. Yeah. Number 14. Find the basis by reduction of order. Basis. Two functions, but the first function in the basis is given. Yeah. This type. Yeah. There is a formula. Yeah. So number 14, you do this. Okay. So second order ODE, but the first solution is given. Yeah. So you need to find the second one. So we have a formula. Yeah. All right. Yeah. Yeah. So here I do not need to give you the details. Yeah. Because we will find the details easily. Yeah. All right. Number 15, solve second order ODE by reduction of order. Yeah. Reduction of order. Yeah. So this one, there are two types. Yeah. But here I like to do the type 2. Yeah. Type 1, I cannot do. Yeah. So this type, because each type we can only do one question. Yeah. We do not have room for two questions. Yeah. So type 1 actually, we did that before. Yeah. Remember? So that's the fx y prime y double prime equals 0. This type relatively easy. Yeah, so I do not need to give you the question. Yeah, because we can introduce a new variable equals y prime. So then first order. Yeah, that's pretty easy. But second type a little harder. So you need to prepare for the second type. Second type, so look at this example. Yeah. This example, the pattern, the format is f of y prime, y double prime equals 0. Yeah. There is no x. Yeah, no x. Yeah. And another thing, it's not necessarily linear, you see? Yeah, this f function, for question like this, usually it's not linear. Yeah. Yeah. But, so we can use a special technique. Yeah. So remember that, chain rule, yeah. So later we will see it again. Yeah. So I show you two examples before. Later, we will use the same method again. Yeah. Yeah. So definitely one question for this type. Yeah. All right. Study and number 16, method of undetermined coefficients. Yeah. All right. Non-homogeneous, yeah, but the ODE, the coefficients for those y terms are constant. Yeah. Constant. Yeah. Otherwise, it's too hard. Yeah. So we cannot solve. Yeah. Constant. Yeah. All right. So there is a r of x function right hand side. So then we need to determine. Yeah. So here. So we need to find a particular solution. The particular solution, we need to choose appropriate form, structure. The appropriate form, the structure, remember there are three rules: basic rules, modification rules, and the sum rule. Three rules. Yeah. The hard part is the modification rule, relatively hard. The other two, straightforward. Basic rule, sum rule, straightforward. But the modification rule, yeah, you need to, when you select, you need to be aware of the specific structure. Yeah. So when I compile that document, I will write comments. Yeah. I will write some comments explaining the main points. Yeah. So that's all right. Last one, question number 17, the last PDE solving question. Method of variation parameters. Still non-homogeneous, but we use formulas. And but when we use formulas, we need to know the basis for the homogeneous solution first. This one, the basis. We need to find the basis of homogeneous solution, y1, y2. Then determine UV function, right? We have formulas for UV function. Yeah. Yeah. UV function and Wronskian, we need to calculate Wronskian of y1, y2. Yeah, so then, you just, plug in, but you need to calculate integrals. You need to calculate integrals. Yeah. And when you calculate integrals, some of the integrals, you need to do, some recursion way. Yeah. In my solutions, I did a few examples. I don't know if you're aware of it or not. Yeah. But in my document, I will mention that. Yeah. There are a few special structure of integrals. You cannot find the integral directly. You have to do the integration by parts twice. So then you get a recursion, because left-hand side, right-hand side, they have the same term. Okay? Yeah. So there you can find the expression of that original integral expression. Yeah. That one. Yeah. So in my review document, I will point that out. Yeah. In my solutions to exercise question, I did a few times, 2 or 3 times. Usually you need to be very patient, to do the calculation. Relatively long, yeah, because you need to do integration by parts twice. So then you can find the integral expression. Yeah. All right. Yeah. So that's the computation technique you may have here. All right. So that's the first type, 7 questions. So practice. So you make sure you feel comfortable. Then the second type, word problems. 8 questions, word problems. 3 in class. 5, you have a few more days to complete that remaining 5 questions. So you won't get too much pressure. All right. So let's look at those 8 questions. Word problems. Question number 18. Radiocarbon dating. Here, although I use this title, radiocarbon dating, we know we use the decay model, and under this model, there are several different type of questions. So I put those different variations under this type, different variation. So not necessarily exact radiocarbon dating. I mean, some other, if we use the same model, so I put on this. For example, this one, moisture. So dryer, this is one of our exercise questions. Because equation the same, the model the same. And the way we solve equation similar. I mean, so the first question I give you this type. This type. It could be radiocarbon, but I try to find one under this type. All right. The first, number 18. Number 19, heating an office building. Newton's law of cooling. Apply Newton's law of cooling. So although I use this title, but we have several variations for under this type. I may choose one of the variations to give you the question. Here, the sample question, I give you a few. This one, we also use the same Newton's law of cooling. But you can see the content of the problem quite different. But the model the same. The equation, the model the same. So I put it under the, you just have one of this type of questions. All right. And another one, our homework question. So you can treat as a variation of that original question. Variation. Okay. The structure the same. All right. And another one. Here, another one. The cake. Cool down. So, and another. Under the same type. Here, have you thought about when you see, because we have seen several such questions in the wording of those questions. Have you thought about, because here we have several places when we calculate the temperature, we won't calculate exact 60 degree Fahrenheit. We just calculate a degree slightly different. Have you thought about that? Why is that? If we look at the previous question here, previous question, we do not calculate the destination degree, exact 22 degree, must be slightly different, 21.9. All right. But actually, you cannot find a solution if you use 22 degree. Yeah. Yeah, because, so think about, when the difference is 0, which E function value gives you the 0? Because we have E to something, right? E to something equal to a number, that number cannot be 0. So we have to take slightly different from 0. Yeah, then we can take natural log. If 0, you cannot take natural log. Yeah. Yeah, so that's the, so in a real world situation, when you see the technical difficult, yeah, because sometimes there is some technical difficulty. So you need to get around it. So this is some way to get around the technical difficulty. Yeah. All right. Yeah. Yeah, another type. So here you can see, yeah, practically, so here, same way. Yeah, we always do like, so we need a small number slightly different from 0. Yeah. Then we can take natural log. Yeah. Yeah. All right. Yeah. Question number 20, mixing problem. The tank, yeah, the mixture, yeah, that one, yeah. Yeah. We have one example we did in class, but we have several. Yeah. Yeah. So here, this lake, yeah, it looks different, but the model the same. Yeah. The model the same. Okay, yeah, and you use the balance law. Remember the balance law. Yeah. Inflow rate minus outflow rate equals the derivative of amount of substance, yeah, certain substance. Sometimes salt, so sometimes here the pollution, substance, yeah, pollution substance, yeah, yeah. That's the y function. Yeah. So that one, yeah. One question for that. Okay, yeah. And later you will see in module 3 we solve linear system. That tank problem you will see, 2 tank. Oh, yeah. Right. 2 tank system. Yeah. 2 tank system. Yeah. So that one, I will also give you that 2 tank question. So you can see this one appears 2 questions. Yeah. One, just one ODE equation. The other one, 2 equation system, linear system. Okay. All right. Question number 21. Undamped forced oscillation with resonance. Yeah. That one, resonance question. Yeah. We do one. Yeah. One question. Yeah. Undamped. All right. Yeah, so the mass spring system, yeah. Damping 0. Yeah. So here, when damping is 0, yeah, then you will have the resonance. So you will, yeah, because the general solution is a periodic function, sine cosine. Yeah. When the damping constant equals 0. Yeah. Yeah. Damping constant equals 0. So you have the equation with the form, yeah, let's see, y double prime plus, some constant ky equals, f function. Okay, yeah. This k positive. Yeah, this k positive. Yeah, yeah, because the spring constant, that k positive. Yeah. So you will see the general solution of the homogeneous part. You have sine cosine. Sine cosine, there is a period. Okay, there is a frequency. That frequency we call the natural frequency. So that when your F force, driving force, has the same frequency as the natural frequency, then resonance occurs. Yeah. So, yeah, that one. Yeah. All right.
My double prime, right?
Yeah, my. So I do some division. Yeah. Do division. Yeah. So we have m originally. Yeah. Here, yeah, simplified in that one. Yeah. All right. Yeah. And another. Yeah. Here, you just look at the structure. Yeah. Not necessarily exact of the, mass spring system. Yeah. Another thing, because this is undamped, then there is a damped case, right? Damped case, sometimes you may have the resonance problem, but sometimes you won't. Sometimes you won't. Okay? Yeah. Only when the homogeneous equation, yeah. So for the damped case, yeah. So what's the damped case? Yeah, here. Damped case, okay? So the equation you will get, yeah, I use the simplified version, cy prime plus ky, okay? F of t. Yeah, I write this, relatively simple version. That's the damped case. You have a C, damping constant C, non-zero C. There, if you look at the general solution of this homogeneous part, sometimes you don't have sine cosine solution, right? Sometimes you have, sometimes you don't have sine cosine. Sometimes you have E function, right? E. When you have E function, it's not periodic. E function, there is no period, right? Not periodic. Then you don't have the resonance problem. Only your general solution, YH, you have sine cosine. C1 cosine plus C2 sine. Yeah. There is a potential resonance effect. Yeah. You need to worry. Okay? Yeah. Yeah. So here, yeah, I remember in one of my questions, yeah, quiz or yeah, I'm not sure. Yeah. I ask you about that. Right? So if you damped, undamped, yeah, the resonance, yeah, there is one question. Yeah. 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 All right. So make sure you know that. Yeah. All right. Number 21. Number 22. Problem RLC circuit. Yeah. This one. Yeah. Another important type. So here you can see, typically I pick the most important question types. Okay. The representative. Yeah. 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 All right. So this is another important type. Yeah. Yeah. So we have the question. Yeah. When you set up equation, so we know for our part, how to represent voltage drop expression, L part voltage drop, and the C part voltage drop. They use that, the theorem, right? Yeah. Kirchhoff's voltage law. Yeah. That one. Yeah. All right. And this context, this electric circuit, this context, you will see another one in the module 3. Module 3 linear system, then we'll do a, double circuit. Yeah, double circuit. Yeah, yeah. Not triple. Yeah, triple, too complicated. So we just do double. Okay. Double circuits. Yeah. All right. Number 23, under-damped. Yeah, so this one, under-damped. Yeah, it's damped, but below the critical line, right? Yeah. Critical damping, there is a, the line discriminant equals 0. Discriminant, yeah, so discriminant, yeah. For the characteristic equation, we can calculate its discriminant, delta, discriminant. Discriminant equals 0. So under-damped, the discriminant is negative. Yeah. So the characteristic equation has two complex roots. Complex roots. So you get sine, cosine. Sine, cosine. Okay? General solutions. So here, under-damped motion and oscillation-free motion. Yeah. Here, so I put these. So here there are two small topics. Yeah. Two small topics, subtopics. Yeah. Under-damped motion, that's one topic. Yeah, yeah, because this one, we want to look at the, the resonance, that point, yeah, critical damping, yeah, that line. Yeah, we want to see that. Another is oscillation-free motion. So here, so they're related. They're related. So I put them together. So what is the oscillation-free motion? Oscillation-free motion. Okay. So when you look at the solution, yeah, when you look at the solution y of t, okay, yeah. Basically, we have two types. Okay, one type e function. Okay. One type E function. Another type C1 cosine, some t plus C2 sine some t. Okay? Yeah. And for the second type, because it's a periodic function, okay? The, displacement, motion, displacement of the, object in the motion. It's a periodic function. When it is periodic, we treat as oscillation, right? Up and down, oscillation. Where the displacement follows E function, there is no oscillation, right? No oscillation, all right? Yeah. So oscillation free, that means we want that type. We don't want this type, okay? But there is a critical line, okay, between these two types, okay? So that line is the discriminant equals 0 line. Yeah. Critical damping, that line. So we need to calculate that line. Above that line, oscillation free. Below that line, oscillation. Yeah. So these two are closely related, but under different names. Under different names. So here I give you two sample questions. In our exercise question sets, we have two examples. The first one, this one, under-damped. Yeah. Yeah. So here, maximum amplitude decreases, maximum amplitude under-damped motion. Yeah. So you have under-damped. When you see this, when you see under-damped word motion, you expect to have second type of solution, under-damped. Yeah. Yeah. Because, yeah, why is that, under-damped? Yeah. Remember, we draw a line, right? Okay. We draw a line, okay? All right. So, over-damped, yeah. Under-damped, and critical damping. Yeah. So this line, critical. All right. Over damped, that corresponds to the E function. Okay. Yeah. Under damped, cosine, sine. Okay. Yeah. Under damped. Yeah. Yeah. So when you see that under damped motion, so you expect to write solution in that format. Okay. All right. Yeah. And maximum amplitude decreases, yeah, because there is a E part. When you write cosine sine, there is an amplitude part. Yeah. You know, this is the oscillation part. Other than oscillation part, there is an amplitude part. Okay? Yeah. So what's that? So usually the structure of the solution is like this. Y of t equals, there is an amplitude part. Then the oscillation part, omega t, yeah, C1 plus C2 sine omega t. Okay? Yeah. So usually the solution has that format. Okay? Yeah. So there is an amplitude part. Yeah. So when you look at the maximum amplitude, you don't look at the oscillation part. Okay? The parenthesis, you don't look at the parenthesis part. You just look at the amplitude part, A part. A. Okay. All right. Yeah. Yeah. So here the maximum amplitude decreases 1/2 initial value. Yeah. So you look at that decrease. Decrease 1/2 because when start at t0, yeah, because usually this amplitude part has the E value, yeah, in that example, E to the negative alpha t. Yeah. When t equals 0, it's 1. It's 1. So you use as the starting point, 1. Yeah. Then, after certain t, because this t, how long? 10 cycles, right? After 10 cycles. Yeah. 1 cycle, 3 seconds. Yeah. From one maximum to another maximum, it's 1 cycle. Okay? One period, 1 cycle, 3 seconds. 10 cycles, 3 times 10, 30 seconds. So at t equals 30, you get a 1/2. Yeah. Because the amplitude decreases to 1/2 of the t equals 0, when t equals 0. Yeah. Yeah. So in that one, so you can find, alpha. Okay? Yeah. So things like that. Yeah. So that's the under damped motion. Yeah. 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 Because here, this kind of details, things, because for the word problem, you need to understand the background, the context, yeah. So how do you connect the content of the problems with our theory? Yeah. So with our, mass spring system, our mass spring, that's our original model. Yeah. So our theory is established on the mass spring system, but here you may not see mass spring, right? It's not necessary, the literally mass spring, yeah, but follow the same model. Follow the same model. Yeah. All right. So that is next, oscillation-free motion. Yeah. Another sample question. Also pretty interesting. Yeah. So you need to be able to recognize. Yeah. So the question, yeah, the word problem is hard to recognize. The question, then the model. Yeah. How to connect. Yeah. So that part, based on your understanding. Yeah. Only when you have a good understanding, you can connect. Yeah. So this one, yeah. This one, the car, okay? Yeah. Damping constant, shock absorber, suspension, yeah, of a wheel of a car. Yeah. So that's the mass spring model, mass spring system. Yeah. Suspension, okay? The wheel, yeah. 4 wheels. A car has 4 wheels. Yeah. So 4, evenly distributed car weight, right? The total car weight distributed on the 4 wheels. Yeah. So, but you need to look at, for each wheel, you get a 1/4 of the weight. 1/4 of the weight applied on one wheel suspension system, local system. So that's a mass spring system. Okay? Yeah. All right. So then, yeah, theoretically, oscillation-free ride. Yeah. So, if you have oscillation, so, with certain amount of oscillation, so when you drive, so you may not feel comfortable, right? Oscillation. So you want, adjust the suspension to pass the oscillation line, okay? Yeah. Above the oscillation line. So oscillation free. Yeah. So no oscillation. Yeah. So then you can, drive smoothly. Yeah. So that your everyday life experience, but you need to connect to our mass spring system, okay? Yeah. In order to answer this question. Yeah. All right. So there, oscillation free, here when you see this phrase, so we go back to the previous slide, under-damped, over-damped, critical line, right? There is a critical damping line, okay? Below critical damping line, under-damped, you have oscillation, okay? So you don't want that happen. Okay? Above the critical line, over-damped, E function, right? The solution E function, so you don't have oscillation, okay? So you don't have that oscillation. Yeah. All right. So based on that understanding, so you can calculate. Yeah. Look at the question. What's the question? What is the smallest value of the damping constant? Damping constant, that's C. Yeah. Remember that damping constant, that's C. Yeah. All right. So here, we go back to the same equation of our mass spring system, Cy prime plus Ky, okay, equals f of t. Yeah. Yeah. This model. Yeah. So this model, smallest damping constant C. Yeah. So the C is above 0, okay? Yeah. Above 0. Yeah. It's non-zero. Yeah. Damping constant. Yeah. If C is too small, yeah, when you calculate the discriminant, too small, you get a negative discriminant, then you get an under-damped system. Under-damped system, you have oscillation. So you don't want that. Okay? C cannot be too small. Too small, you have oscillation. So C should be, you need to raise C a little higher, damping constant higher. At the critical line, that's the smallest C. Okay? Critical line is the smallest C. Above critical line, yeah, you have some cushion. Yeah, you have some room. Yeah, yeah. So the critical line, the borderline, so the question asks you for that borderline C. Okay? Yeah. So only when you understand this whole story, yeah, then you feel comfortable. So when you solve it, yeah, because you know everything. You know all the relationship like this. Yeah. So then you feel very comfortable. Okay? Yeah. So when you write equation, it's not a guess. Right? Because you know what they are doing. Yeah. So you have confidence, write down your equations. Yeah. So that's the, what we want to get in this midterm. Yeah. 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 All right. Yeah. So that's the word problem. So you need to really understand things a little deep. Yeah. Okay. So not just randomly. Yeah. Something similar you may pick the wrong equation, right? The wrong model. Yeah. Sometimes you choose the wrong model. Yeah. Damp it, over damp it, under damp it. You may choose the wrong one. Yeah. Yeah. All right. Number 24. Mixing problem involving two tanks. Yeah. So this time, linear system. Yeah. So here you can see, among all these 15 questions, for the linear system, our module 3 computation questions, I only give you the last two questions, number 24 and number 25. Yeah. Before that, there is no linear system questions. Yeah. Just give you some time to prepare yourselves to feel comfortable for the linear algebra. Okay? Yeah. So here you can see not too much linear algebra. Okay? So I delay. So when we do our final exam, then we have a little more linear algebra. Okay? So this midterm only last two questions. So here I'm talking about those 15 questions, not the top 10. Top 10 we may have a few concept questions related to module 3. Yeah, module 3. Yeah. And because remember our first 10 questions, that's our quiz 3, right? Quiz 3 is supposed to cover module 3, right? Yeah. So mainly about module 3. Yeah. But on the other hand, because it's midterm I have to so I can choose a few questions from module 1, module 2. Yeah. Yeah, but at least 60 to 70% module 3. Yeah. 60 to 70% module 3. Yeah. Yeah, 3 or 4 questions. Yeah. Very likely 3 questions from first two modules. Yeah. Yeah. All right. Yeah. So our homework 2 I haven't assigned. Okay. Yeah. Here, because I will assign your homework 2 soon. Yeah. 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 So you have time. You have the spring break. Yeah. So tomorrow, Friday, I try to assign tomorrow. Yeah. Today is hard. Yeah. Today after the class, I won't have time to make homework 2. Yeah. Yeah. All right. So one like this. Okay. You need to set up equation using the balance law. Okay. For the first tank, by balance law, one equation. Second tank, by the balance law, second equation. You have a linear system. Okay. Yeah. So it's a good question. Yeah. Yeah, not too complicated. Yeah, hopefully. Yeah. 2x2 matrix, not too complicated. Okay. So the last question, electric circuit question, but with 2 circuits. Yeah. Electric network, 2 circuit. Okay. Yeah. Yeah. So 2 linear equations, I1, I2. Okay. Yeah. Yeah. Eigenvalue, eigenvectors, yeah. Initial conditions. Yeah. Yeah. Here, general solution, yeah, but possible initial conditions. Yeah. So these last 2 questions, linear algebra, yeah. Just the eigenvalue, eigenfunction you need to calculate. Yeah. For 2x2 matrix. So after that, write the general solution. Yeah. If you have initial conditions, then you need to plug in to find C1, C2. Yeah. Yeah. So that's all 15 questions. Yeah. Yeah. So in class, yeah, we will have break soon. Yeah. In class, I'll give you three word problems. So I like to pick each module 1. Okay, module 1, 1, module 2, 1, module 3, 1. Okay? Yeah, so then the remaining 5, yeah. Although on the test paper, I put there, yeah, because some students, if you have, after you finish first 10, you have extra time, so you can, if you like to do, you can do it. Okay? Yeah, but if you feel too tired, so you can go home. So, yeah, let me tell you how much time I like to give you. Yeah, because that test day is Thursday. Yeah, Thursday already. Okay, Thursday, Friday, Saturday, Sunday. I give you end of Sunday to submit. The last 5 questions, solutions. Yeah, plenty of time. Plenty of time. Yeah. Yeah. So do not feel panic. Yeah. So not that bad. Yeah. Any comments? So you see the whole picture of this midterm. Yeah. Yeah. All right. That's it. Let's take a 10-minute break, and we will start at 7:15.